Hello and welcome to this week's video. Today is slightly unusual compared to my other videos. I thought it might be fun to look at questions maybe from Classical Electrodynamics by Jackson. Starting in the middle of the book, this is chapter 10. I've been looking into magnetohydrodynamics recently, and this is the first question in the chapter. Depending on how we are for time, I will look into doing the other ones as well. But we will begin with this. So I'm sure you can all read, but regardless, the question reads: an infinitely long solid right circular metallic cylinder has radius capital R/2 and conductivity sigma. It is tightly surrounded by but insulated from a hollow cylinder of the same material of inner radius R/2 and outer radius R. Equal and opposite total currents distributed uniformly over the cross-sectional areas flow in the inner cylinder and in the hollow outer one. At T is equal to 0, the applied voltages are short-circuited. And part A asks to find the distribution of magnetic induction inside of the cylinders before T equals 0, which is the initial steady-state magnetic field, which we can find using, I think it's Ampere's law. Anyway, we'll begin. Before it's short-circuited, we just have a steady DC current flowing through the cylinders. What we want to find is the magnetic field, so we'll call that B phi, and of course that's R as its input. So using Ampere's law initially, which states that dl is equal to mu naught and then times the current enclosed. I'll just do I sub E for that. Thus this is also times 2 pi R is equal to our magnetic field, so B sub phi R times 2 pi R is further equal to mu naught I sub E. Now we know the total current is I, so we can say some uniform current density, which can be J1. That's equal to I over pi R over 2 all squared, which is just 4I over pi R squared. Yeah. And for some radius R, which we've already established inside of that region, the current enclosed is, as a function of R, should be J sub 1 pi R squared, which is 4I R squared over large R squared. Why not little one? And now we apply Ampere's law here. Hence B phi R is equal to mu naught over 2 pi R times 4I R squared over R squared, which is 2 mu naught I R over pi big R squared. Should probably define a range for that. Yeah, I didn't think of that. Between R over 2. Okay, good. Moving on. Now we need to do the outer cylinder, because this is just the inner one. The total current density here is minus I. So we can again define a uniform current density J2, which is, I'm going to start the denominator, r over 2. You can of course see symmetry here from our previous one, which is minus 4I over 3 pi big R squared. The enclosed current includes the entire cylinder's current plus the fraction of the outer cylinder's current in this circumstance, so I of R is equal to I plus J sub 2 pi R squared minus R over 2 squared, which is I minus that 4I over 3 R squared because the pi's cancel out, times R squared minus, oh, why has it done that? R squared over 4, which is, I'm going to do it in steps, minus 4, so I don't make a mistake, squared R squared plus I over 3, because, yeah, I could get this right, which is 4I over 3, 1 minus R squared over R squared. Great. Now we plug this into, or reapply Ampere's law again. So B sub phi of R is mu naught over 2 pi R times 4I over 3, 1 minus R squared over R squared. Ugh. Stupid brackets. Which should yield a similar-ish result to the last one. If I use my brain, 2 mu naught I over 3 pi R times 1 minus R squared over R squared. Right. And this is for R over 2 is less than R is less than big R. Cool. And so we have successfully found the distribution of magnetic induction. These are our distributions. It would be piecewise, obviously, because there's two different cylinders. But that is a success, I hope. If I've made a mistake, let me know. Comments exist. But please be nice. I'm not the best at this. Anyway, moving on, let's take a look at part B. So part B further asks us to find the distribution as a function of time after t equals 0. Ignoring displacement current, which is very kind of Mr. Jackson. So that makes Maxwell's equation slightly easier here. We're only going to take the curl ones into account. So del cross E is minus partial B dt, and I realize that should really be a vector. I'm a bit lazy about doing that. As we got from the question, they have conductivity sigma, so mu naught sigma E. And as is sort of standard to form some useful equation, we take the curl of both sides. I've done this about a bajillion times now. So of this equation, so square B is equal to, and the curl of V is just that. And minus sign somewhere. There. Mu naught sigma B. Obviously, those would cancel out. And that's wonderful. Now we ought to convert to cylindrical coordinates, which is equal to B phi RT and then our phi normalization vector constant thing on the end. We get that d squared b phi dr squared plus 1 over r db phi, just completely missed there, dr minus b phi over r squared is equal to mu naught sigma db phi, sorry, over dt. Brilliant. Now to solve this, we will separate variables. A foolproof way of solving second order partial differential equation, but same thing in principle. Now, if we split it into two, so b sub phi of rt, if we let this equal, let b sub phi rt equal to r of r times t of t. Now let's substitute. So t of t is then proportional to e to the minus t over, I'm just going to call it tau, and tau is equal to mu naught sigma over k squared, k something, and then we get an equation which might look somewhat familiar. I feel like I'm working bits of this out in my head, and I'm just trying to make it make sense, as they say. Anyway, this is Bessel's equation. And so the solutions to this are J1. I shouldn't have used J1 for the last one. Realize that now. The solutions to this are, of course, Bessel function of the first kind, which is J1 of k times r. Now, we know that the initial current is 0, and there's no extra current, so Ampere's law requires that this equals 0. Thus, the Bessel function is also equal to 0 from that, and so also kn equals xn over r. These are the roots of the Bessel function, which I'll find eventually. When it's equal to 0, of course. The general solution then is b phi rt equals 1 to infinity a sub n j sub 1 kn r exponent of minus kn squared t over mu naught sigma. Nice. So this is our general solution, at least. We now, this is the bit of all bits, is the actual solving. There's going to be a lot of things, and I might not explain everything in detail, but essentially the entire point of this is to try and work out what AN is. And it is certainly a thing. Let's use orthogonality. So AN is equal to, I'm going to start with the denominator, the Bessel function second kind of KNR squared, all of that's over 2, times the integral, not a nice integral, there we go, from 0 to r of r b phi r0 j1 kn r dr. There's three Bessel identities I'm not going to write out, but they're useful here. The first one states that the integral of x squared j1 of x dx is x squared j2 of x. The second one is that the integral of j1 of x is minus j0 of x. And the third is that j0 of x plus j2 of x is 2 of x j1 of x. That's a really cool way of proving that last one. Anyway, I won't get confused. Let's evaluate the inner integral from 0 to I over 2. So this is I1. I have N1, because I'm going to use I1, I think, is equal to the integral from 0 to R over 2 of R 2 mu naught I R over pi R squared J1 K N R dr from the above. We can pull all of this out, or bits of it out at least. R squared, so the integral from 0 to R over 2 over R squared J1 K N R dr. Let's do a U sub. U equals to K N R d R. No, du dr equal to I'm going to write it out like that. Dr is du over k sub n. R squared is u squared over k sub n squared. I think that is an okay u sub. I of n1 therefore is equal to 2 mu naught I over 2 pi r squared k n cubed times the integral, there you go, from 0 to k n r over 2, can't forget about bounds, of u squared j1 u. Here's where our first identity comes in useful. This is 2 mu naught I over pi r squared k sub n of u squared j2 of u between 0 and k n of r over 2. Summing that in, 0 is fairly easy, so it just becomes 2 mu naught I over pi r squared k cubed times k n squared r squared over 4 times j2 of k sub n r over 2. That's pretty good, apart from my bracket, which isn't. Stuff cancels. Leaving that alone, you get a 2 in the denominator. Nice. Just checking that I haven't made a silly mistake. Okay, and j2. Cool. Now we just have to do the outer integral, which is I of n2. Very much similar-ish kind of thing, but we end up with a different identity. In fact, it's slightly easier. From r over 2 to r of r times 2 mu naught I over 3 pi r times 1 minus r squared over big R squared. J1 kn r dr. Cool. Pull it out again. 2 mu naught I. It's very formulaic, this. 3 pi r squared, but it's sort of knowing what to do when is the bit that, goodness gracious, it's the bit that I really, it took time. It took me a while to work out how I was doing these. I'm not solving them now. I made notes and I know what's going on. It's practice, I guess, and also showing off. Showing off? I don't know if this is an apt way of showing any particular skill. It's more just, I can do a problem if you give me enough time and an entire book about how to solve it. Anyway, 2 mu naught I over 3 pi, that got oddly philosophical. R squared integral r over 2 to r of j1. In fact, there's not even an identity. No, there is. Did I point it out very clearly? No, there is no identity. Apologies for the confusion. Nearly ran out of space there. Anyway, same u sub from above. E equals k and r dot dot dot. But let's make it clear that the dollar is afterwards. Anyway, I might need a bit of space for this because it really does get gross. 2 mu naught I 3 pi r squared. I forgot the big brackets. R squared over kn 2 kn r, using various. So this is our second identity and this is our first identity. I won't repeat them. I can repeat them. This one is just equal to minus j0, of course, and that's j2. And then I think it becomes fairly clear as to what we're going to use the final identity, which is j1 plus j2 equals 2 over x j1. All of those parameters being x. Parameters. Doing too much C coding recently. Is equal to minus 2 mu naught I over 3 pi r squared k, and this is really quite a mammoth of a thing, so I'm going to write really small. R squared j naught k n minus r squared j. See what I mean when I say it's very formulaic? It's like identically looking stuff. I mean, obviously that term's going to look very similar to the last one. No surprises there. I can simplify that a bit more. Minus 2 mu naught I over j2, okay. Put the bracket there. Minus j naught kn r over 2 plus a quarter j2. Did I pull out? Yeah, I did pull out the r squared. Good. Beautiful. Need to stop saying all the time. Oh, I think I'm a bit loud. That's alright, I'll adjust that in post, as they say. Remembering our third identity here. This is J0 of KNR plus J2 of KNR is equal to 2 over KNR J1 of KNR, which is great. KNR, which is great because we already have this. And that applies to the first term, for which Kn satisfies our boundary condition from earlier, and hence that whole term vanishes. Yippee! As the German TikTok child says when his mum lets him drink cola and play Fortnite. Niche cultural reference there. So this is 2 mu naught I over 3 pi kn. I feel like I have to justify that that's only niche to the people who would have been 26 minutes into a video solving a problem from classical electrodynamics. I'm sure most people my age would know exactly what I'm on about. Kn r over 2 plus a quarter J2 Kn r over 2. Brilliant. Now, of course, we have to find the total. So In plus In2. What do we do? Add them together. This is, gotta try and remember this. Mu naught I over 2 pi Kn J2. Mu naught I over 2 pi Kn J2 of Kn r over 2, I'm guessing. I guess correctly. Plus this, and I dare to expand this. 3 over 2/3 even. There's more though. Mu naught I over pi Kn J naught Kn r over 2 mu naught I pi Kn J2 Kn r over 2. Okay, continuing on, pulling out. No, I'm just going to make it big. 3. R over 2 plus, so that's a half of that, and that's a sixth, so what's a half plus a sixth? Wait, that's 3/6 plus 1, 4, 2/3. Okay. Right, good. That's what I was hoping for. My theory that as you get more advanced at maths, your mental maths gets worse prevails, or maybe I'm just stupid. I don't know. I'm not exactly old, so I can't put it down to memory. Anyway, all I've done there is factor out the 2 over 3 mu naught I, 2 mu naught I over 3 pi Kn. And we have something that we could use that identity on. So this is just 2 over that, so it's 8 mu naught I over 3 pi r k squared n times j1 kn r over 2. Right, and now we have to substitute this back into an, which we have up here. We've solved that integral. I should have said that I've equated that to I n. So an is 2 over r squared j, that's not much for j, is it? j2xn squared times that 8 mu naught I r squared, don't forget that, over 3 pi. I can actually, sorry, I can actually cancel that, I forgot. Doesn't matter. j1 xn over 2, which is, goodness me, prepare, 16 mu naught I, I'm going to leave them as a separate fraction, over 3 rx squared n. Yep, times j1 of xn over 2 over j2 of xn squared. Yes! And so we can put everything together and conclusively state that b of phi regarding time and disregarding the displacement currents is 16 mu naught I over 3 pi r times the sum from n equals 1 to infinity of j sub 1 xn over 2 over j sub 2 xn squared times x n squared j1 xn r over r times the exponent of the bit from the beginning, which I believe is minus x squared nt over mu naught sigma r squared. Ta-da! That is the solution. I'm not going to box it because it's not a boxable kind of thing, but that is hopefully correct. It aligns with what my notes say. I don't know if there's answers to the classical electrodynamics book. Who knows if it's right? I don't think there's answers, unless they're in the book, but I just haven't looked for them enough. Anyway, there is a final part, which is less mathsy. I had another question lined up, but I'm not going to bother. What is the... maybe I'll do it in a future video. This was actually quite fun, quite a nice change from doing like a derivation or something. Anyway, the final part asks what is the behavior of the magnetic induction as a function of time for long times. Now, right, let's get back down. If we have a spatial mode, n, then this has a characteristic tau of n, which is equal to mu naught sigma r squared over xn squared. Now, we know that for each root of our Bessel function, they increase. So x sub 1 is less than x sub 2, is less than x sub 3, etc., etc. This decay This is the characteristic decay constant. Sorry, I should have said that. It increases, obviously, because if this is decreasing, if this is, that's okay. All right, sorry. Recompose. Tau of n is the exponential decay time constant, right? And I mean, I showed that earlier when it was the t over tau. Now we know these roots increase, so the decay times decrease as n increases. So as n tends towards infinity or whatever, tau of n gets smaller. So we have a definition mathematically of what a long time is. It's not the most amazing thing, but it's okay. So we say that a long time is a time on the order of or greater than the longest fundamental decay time constant, t. So we can say that a long time is approximately greater than t1, tau 1 even. And then if t is significantly greater than tau 2, all higher order spatial modes decay rapidly compared to the fundamental mode, which is tau n equals 1. You can treat this as if the system forgets the complex initial step function geometry that was sort of there and relaxes into this fundamental mode n equals 1. And so at long times, the induction behaves just as an exponential decay. I don't know if you've seen an animation of the Bessel function, but you can kind of guess it from that, as long as you have this kind of idea. And so we can actually just cut out the sum and only do for n equals 1. And doing that... Oh no, that's so annoying. Oh, it's just out of view. It's fine. This can be rectified with ease, actually, by moving that over there and moving that up a little, and then moving this whole thing up a little. Yay, nothing is a problem. So hence we can say for long, I forgot to write c there, times, therefore b phi of rt is roughly equal to 16 mu naught I over 3 pi r x squared sub 1 times j1 x1 over 2 over j2 squared. I need to put that. That's okay. Squared all of this times j1 x1 over big R times the exponent, this is our exponential decay factor, x1 squared t over mu naught sigma r squared. Yay. Right, and hence we have an approximation for long times. Obviously this isn't perfect, but it's a million approximation. This is perfect and also quite horrific. But yeah, it was nice to do a change of video where I'm not just doing a derivation or something, I'm actually solving a problem. I hope that you found it interesting. I hope this was useful to anyone who doesn't understand this question. It's obviously taken quite some time to go through, and I feel sorry for anyone who's had this on a problem sheet on their homework and is scrambling trying to find a solution because they realised that they're not going to have enough time to finish all the questions. Anyway, have a nice week, and I will see you next week. Goodbye.